Okay, this practice sheet is, of course, on refraction and light changing mediums. So let's look at this a little bit. The first one here, blue light goes into material with index of 3.45. What's the new speed and wavelength? Okay, well, relatively straightforward. Okay, if it's going into something with a higher index, we'll assume it's just starting in a vacuum. The higher the index, the lower the speed and the lower the wavelength, just at the same ratio of the index. So if we go back to the basic definition of how to find this, we have Vx is equal to c divided by nx, and you've got the index, so you should be able to find the speed relatively easily. Wavelength, very similar. If it's going 3.45 times slower, the wavelength is going to go down by a factor of 3.45. So very similar calculation, and you can get the new wavelength of the bluish light. All right. So light goes into glass. What is the angle in the glass? This is just a basic application of Snell's law. It doesn't say anything about the initial stuff, so we'll just assume it's like a vacuum or air. No big deal. So we need to just use Snell's law. So of course, n1 sine theta 1 is equal to n2 sine theta 2. We assume the first stuff is air, no big deal. So then we can just apply Snell's law. Coming into 45, n value for the first material will be 1. We know the angle has to get smaller, so it's going to be smaller than 45, and should be relatively straightforward application of Snell's law. Light's got a wavelength of 425 nanometers in water, and a special plastic. It travels at 1.78. What's the wavelength in plastic? Okay, well, a couple ways we could actually do this. It doesn't really make a difference, but you might want to find the index for the second material, the plastic, and you can find the index for the plastic would be the speed of light in a vacuum divided by the speed in the plastic. So you could find the index. The index, of course, is always really handy. And then a lot of this actually has to do with the ratios. Now, of course, the light has a wavelength of 425 nanometers in water, not in air or vacuum. So the first index doesn't have a value of 1. It's the index of water to be 1.33. But you can just use basic ratios to actually figure out what the new wavelength would have to be. And if we go back to the way we derived Snell's law in the first place, it was all about ratios. And one of the ratios would be lambda 1 over lambda 2 is equal to n2 over n1. And just cross multiply and divide and figure it out. Of course, the 1s and 2s are flipped because, of course, as the index would get higher, the wavelength would get shorter. So why not find the index of the plastic and then use a basic ratio in order to figure out what the wavelength in the plastic would be. All right, next we got the angle of light when it goes into CS2 is 12 degrees. What is the angle in air? All right, so it's 12 degrees at the very, very bottom. And this is like a double Snell's law question. That's all this is. So, you can start in the CS2 with an index of 1.6, do Snell's law, work your way backwards, get the angle in air, and then, or not in air, in water, and then do Snell's law again, working backwards to find out what the angle must have been in air. So basic Snell's law twice. That's all we have to do. All right. Then number 5. We've got light starts in air, and then it goes into a block where it travels at 1.3 to the 8. So what you could do is you could find the index for the block. That might come in handy. They're going to find the 4 labeled angles. So find the index of the second material of the block. Then use, it starts in air, so the index for air. Use Snell's law to figure out what the second angle would be, and then it's basic geometry as to which angles would belong where. Okay, so that should work out really nicely. So some Snell's law, some ratios, and that's all we need to do for this sheet.